Hello everyone, my name is Yushi Wei and I'm a PhD student from the Hong Kong University of Science and Technology Guangzhou. Today I'm honored to present our work. This work is a collaboration with Xinru Chen, Rongkai Shi, and my supervisor, Professor Haining Liang. In this talk, I will introduce how we rethink reorientation in teleportation by leveraging bare hand gesture, enabling users to control their facing direction naturally and efficiently without relying on controller-based input. First, teleportation is one of the most widely adopted locomotion techniques in virtual reality systems. It minimizes cyber sickness, requires little physical space, and works well across many applications. In commercial VR systems, teleportation is often combined with reorientation, allowing users to specify their facing direction after teleportation. This reduces the need for physical turning and improves navigational efficiency, especially in seated or spatial-constrained environments. For example, many commercial VR games and VR applications integrate orientation adjustment directly into the teleportation process. However, despite its widespread use, reorientation-enabled teleportation remains underexplored in research. Most previous studies emphasize translation, where reorientation is treated as a secondary component. Furthermore, the majority of existing solutions rely on controller-based input, such as joystick or touchpad. This controller-centric design tightly couples reorientation to devices' specific input mechanism, leaving devices free interaction remain underexplored. At the same time, bare-hand interaction is becoming increasingly mainstream due to advances in hand tracking technology. Previous research shows that bare-hand input enhances embodiment, strengthens body ownership, supports more coherent spatial understanding, and reduce cognitive translation cost compared to controller-based interaction. However, when it comes to reorientation-enabled teleportation, only one bare-hand technique has been proposed and is lack comprehensive evaluation. From our review, we identified four main gaps. First, reorientation is widely used in commercial VR systems, but relies study as an independent design factor. Second, there is lack of clear design guidelines for efficient and user-friendly orientation. Third, most existing techniques are controller-centric, limiting board applicability. Finally, bare-hand reorientation remains largely underexplored and underevaluated. In that case, this leads to our central research question: how we can design reorientation-enabled teleportation technique that fully leverage bare-hand interaction while maintaining efficiency, usability, and user preference. To answer this research question, we designed four bare-hand reorientation techniques. The first technique is called current waist rotation and builds up on the earliest bare-hand reorientation mechanism introduced in previous research, which determines facing direction through waist rotation. In this technique, users rotate their waist while positioning the destination, adjusting orientation and the destination simultaneously. The second is decoupled waist rotation. Position and orientation are separated into two sequential phases. Users were required to first select the destination, and then they can independently adjusting the orientation through their waist. The third is joystick waist rotation. Waist rotation beyond a threshold triggers continuous turning, with turning speed modulated by hand depth, similar to joystick-based control. The final one is direction drawing. After selection the destination, users drag their fingertip toward to directly indicate the final facing direction, creating a natural spatial mapping between gesture direction and orientation. To evaluate the effectiveness of four techniques, we conduct a controlled user study with 24 participants using a within-subject design. In each trial, participants were required to align both position and orientation with the target ring. The target appeared within a pre-designed area. Participants teleported via a pinch gesture. select the destination using hand-ray, adjusted facing direction using the current technique, and confirm teleportation. Each technique involved 15 trials, resulting in total of 4,800 trials. All results reveal clear performance trade-off across 4 techniques. First, the concurrent with the rotation was the fastest technique, but it also produced the largest distance and orientation error. Because position and orientation were adjusted simultaneously, precise refinement became difficult. Despite its low accuracy, many participants still describe this technique as efficient. They often accept small alignment errors in exchange for faster interaction. And the decoupled with the rotation reduced both positional and rotational error compared to the concurrent one. But this improvement came at the cost of longer computing time due to the sequential interaction structure. And next, the joystick with the rotation achieved the lowest orientation error, demonstrating high precision. However, this precision required the longest computing time and orientation adjustment duration. Subjectively, this technique also imposed a higher mental and temporal demand, and it was least preferred technique overall. Many participants perceived it as accurate, but slow and cognitively demanding. And finally, the direction drawing provided balanced performance across metrics will not always be absolute best in every subjective measure. It avoided extreme trade-off and maintained strong overall efficiency. Subjectively, this technique received the highest rating in user experience. Most participants ranked it within the top 2 positions. Frequently describe it as intuitive and natural use due to the direct spatial mapping between the gesture direction and the facing direction. From this finding, we derive 4 design implications. First, efficient may be more important than perfect precision. Users often tolerate a small error if interaction feels fast and fluid. Second, intuitive direction mapping significantly improve user experience. Natural spatial correspondence reduce learning cost and enhance control. And third, discrete orientation mechanism may be preferable to continuous rotation control for short, frequent teleportation tasks. And finally, user preference may different. Some users more prefer speed, others value stability or precision. So we should provide flexible interaction options. In that case, we can accommodate diverse users' needs. In summary, we systematically evaluate 4 bare-hand orientation techniques for teleportation in VR. Our findings review key performance trade-offs and provide actionable design guidelines for more efficient and intuitive orientation control. We hope this work can inform future user-centric locomotion design in virtual reality systems. Thank you.